Hey everybody, it's Mr. N, and we are going to do the next lesson, which is congruence and transformations. So let's talk about what the congruent symbol is, which you should already know by now. And the congruent symbol looks like this. It's an equal sign with a mustache. So congruent means same size and same shape. So when we name congruent figures, they are going to correspond to each other. So like in this figure, I will say triangle ABC, and if it's congruent to triangle DEF, that means that all these corresponding parts will be congruent to each other. So I can just by name look at it and know what will be congruent to itself without even looking at the diagram. So in other words, AB right here will be congruent to DE. If you look, AB congruent to DE. BC will be congruent to EF. If you look, BC, EF. So you can see all the different congruent parts. You could say AC congruent to DF. AC, DF. Now you could do angles. Angle A would correspond to angle D. So B would be E and C would be F. So the way we name it here must correspond to what's congruent there. So if I say ABC, I'll say DEF. Next, we have these transformations, and one-to-one will just mean that if I move it left, right, up or down, stretch or rotate, it will match exactly. So we need the image, the pre-image, and then the mapping. If the two are congruent, so if the pre-image is congruent to the image, then we call this an isometry. And isometry is just the fancy word we used for congruence, which is another fancy word for rigid transformation. So all those mean the same, and here it is again, talking about that. Now we can get into detail here and say that an isometry maps a triangle to a congruent triangle. So you'll have the same exact triangles, just in different spots. An isometry maps an angle to a congruent angle, polygon to a congruent polygon, and etc. The one that is not an isometry is a dilation, and we'll talk about dilations in a different section, but that one won't be an isometry because you're actually going to change the size of it. All right, let's take a look at the next page. Let's enlarge this so we can see a little bit better. Here are the ones we've talked about already. We have a translation, a reflection, a rotation. We did these different rotations. We did 90, 180, and I also added 270 for you. Let's put it on here. Well, it is kind of on here already with this one. This is the clockwise version, so this is 90 degrees clockwise. If I go counterclockwise, this would be the 270 degrees. So this one would be XY 270 would map the same thing, negative y x. Here we have the 180, which we said is the same as a half turn. Here's the dilation, but again, we're going to talk about this one a little bit later. But basically, we just have a scale factor here, and we're multiplying the x and y by something. Okay, then we've got a couple theorems we can talk about. For this first one, let's move this over here. A composite of two reflections in two parallel lines is a translation. The translation glides all points through twice the distance from the first line of reflection to the second. I'll explain this one to you right now. Suppose I draw these two parallel lines like this, and I'll say L is parallel to M. And I've got a point right here. Actually, let's make that a little bit closer right now, right there. If I'm going to reflect this across this line first, so I take that distance and I go that distance right there, and then I'm going to reflect it across this line. So I'm going to reflect it to here. Whatever this distance is, it has to be the same on the other side. It's saying that I'm reflecting it twice the distance between these two lines. Well, let's just see how that works. So zoom in a bit here. So if this distance right there was x, that distance would be x. If this distance was y, that would be y. the distance between these two lines is x plus y, and the distance between the 2 points now, after all that, would be 2x's and 2y's right here. 2x's and 2y's. That would be 2x plus the 2y. So that's why this theorem says it's twice that distance from the first line to the second. Okay, let's move on to the next theorem, and the next theorem says a composite of reflections in two intersecting lines. So here was the situation where we had two parallel lines, but what if these two lines intersect? We'll call these lines J and K in this diagram. Two intersecting lines is a rotation about the point of intersection of the two lines. The measure of the angle of rotation is twice the measure of the angle from, that should say from, not form, the first line of reflection to the second. So here's what I'm saying. Let's go back to the parallel version. If I have the two lines parallel, then this distance we said from point A to A prime, the double, or A double prime, because that was a double reflection, will be twice the distance between these two lines. But what if these two lines intersect each other? If these two lines intersect each other, here's point P. I'm going to take this distance P, and it doesn't look so great in this diagram, but we're just going to do it. And there's P prime. And then we're going to do it the other way, like this, and right there. So that's P prime. Take that distance, make it there. That's P double prime. So what ends up happening, I measure this angle, and since these two distances are the same, these two angles right here, 1 and 2, will be the same. If this whole thing is called y, y will be made up of angle 3 and angle 4, but those two are the same because these two distances are the same. So since angle 3 and angle 4 are the same, 1 and 2 are the same, the whole thing right in here will be twice whatever angle y is. Because these two are the same, or these two are the same right here, and those two are the same. So a reflection about K and J, this composition, will be a reflection about point O twice whatever angle y is. Okay. Let's move this up. For some reason. Here is how your book will show these in big ideas, and that same one right there. So it'll be twice whatever they're calling this angle x, twice whatever it is right here, and they're calling this distance d, and it'll be twice whatever that distance is. So I showed it to you just a little bit different so you have a second way. Let's move on to the next page. All right, so we will do these student journal problems in class, but let's do a few additional examples here. So on these questions, for number 1, it says point M is xy, and we need to make this transformation and find out what the new, or M is the transformation, sorry, such that xy maps to x plus 4, y minus 3. They want us to find the new points. So A prime would be 3 plus 4, which is 7, and then 10 minus 3, which is 7. B prime would be negative 6 plus 4, which is negative 2, and 4 minus 3, which is 1. And C prime would be negative 1 plus 4, which is 3, and then negative 4 minus 3, which is negative 7. Here, notice there is a scale factor on it. And this is just a translation, this first one. For the second one, we're just going to do this and determine what P prime is. So that would be 2 times x, so that would be 2, and negative 3 times y, or negative 2 times y, which is negative 3, so that will be negative 6. Q prime would be 8, 2, and R prime would be negative 4, negative 2. Now it says, describe the transformation. Well, this is a dilation. And again, we will talk more about this later, but whenever I'm multiplying, it's a dilation. And the fact that these are both twice, keeps that consistent scale factor. Okay, so these are the same. I'm going to skip down to a couple of these problems right here, and I will do these ones down here. And these are similar to the problems that we've already been doing. If the coordinates here for B, is 2, or this is going to be 1, 2, 4, 1, 4, and A will be at negative 1, 2, 4, 5, and C will be at negative 2, negative 2. I can find my A prime, and A prime would be negative 1 minus 2, negative 3, and then 5 plus 1, which would be 6. B prime would end up being at 1 minus 2, which is negative 1, and 4 plus 1, which is 5. And C prime would be negative 2 minus 2, which is negative 4, and negative 2 plus 1, which is negative 1. This is a congruence transformation because all we're doing is a translation. We are not multiplying the x and y's by anything, so it's going to preserve the congruence, and it will be an isometry. All right, so we'll just leave it at that because these other examples we can do in class, and you've done stuff like this before. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.